Alright, today we're going to be talking about power functions and polynomial functions. So let's look at the expression, how many variables, what its classification is, if it has a special name, and what's the degree. So this expression, I don't know why the 7 is to the side, but it still belongs to this. How many variables does it have? It has one variable, just at different degrees. Is it a polynomial? Yes. If it's a polynomial, how many terms are there? Well, there's 1, 2, 3, so it's a trinomial. Tri meaning 3, nomial being name or term. What's the degree of the polynomial? The highest power is 2. So this one right here, y minus 2.5. How many variables? 1. Is it a polynomial? Yes. How many terms are there? It's 2, and its special name is binomial. Bi meaning 2. What's the degree of the polynomial? Well, remember there's an implied 1 here, so it's a degree 1. Minus 5x squared times y. How many variables does it have? It has x and y, so 2 variables. Is it a polynomial? Yes. How many terms are there? Just 1 term. And we call it a monomial, mono meaning 1. What's the degree of the polynomial? Well, this is 2 and this is 1, so 2 plus 1 gives me 3. This 4x squared minus 2 over x cubed. How many variables? 1. Is it a polynomial? No, because there is a fraction with a variable in the denominator. This is b cubed plus 1/3 b squared minus 1/2 b plus 12. How many variables? 1. Is it a polynomial? Yes, because there are fractions, but the fractions don't have variables in them. How many terms are there? 1, 2, 3, 4. We normally just call anything more than 3 polynomial, but this calls it a quadrinomial. And what's the degree of this polynomial? There's 3. 3 is the highest power. This one, x is a minus 2 minus 3xy minus 10y squared. How many variables? 1. No, that's not true. There are 2 variables. That's from your book, because there's an x and a y, right? There's 2 variables. And is it a polynomial? No, because there's a negative exponent. And a negative exponent just means it's on the wrong side of the fraction, which means there's a fraction. Okay, so now that was fun. Let's look at the graphs of x squared, x fourth, and x to the 6th. So x squared here is this teal colored one, and then x to the 4th, it flattens out, and then x to the 6th, it flattens out more in the bottom. So all of these have the same general shape, and they're all even, because you can reflect it across the y-axis. X cubed, x to the 5th, x to the 7th are generally the same graph, just spread out more the bigger the exponent. And these are all odd functions because they're symmetric with about the y-axis. Power function, let's talk about that. A power function is a function that can be expressed in the form k times x to the p power, where k and p are real numbers and k is known as the coefficient. So is 2 to the x a power function? The answer is no. A power function contains a variable base raised to a fixed power. This function has a constant base raised to a variable power. This is called an exponential function, not a power function. So which of the following functions are power functions? So we have a constant function, identity function, quadratic, cubic, reciprocal square root function, square root, cubed root, and they all are power functions. Let's see, that's really all, and this kind of explains why. So sometimes we don't really care what happens in the middle, we just want to know what happens with the end behavior. So when the graph is pointing, where is it pointing to? So as you see, that it gets flatter here in the middle, but all of these functions are pointing towards, in the y direction, towards infinity. Okay, so to describe the behavior as numbers become larger and larger, we use the idea of infinity. We use this symbol for positive infinity and this for negative infinity. When we say that x approaches infinity, that can be symbolically written as x with an arrow to infinity. We are describing a behavior, and we're saying that x is increasing without bound, okay, to infinity and beyond. With the positive even power function, the numbers you put in increases or decreases without bound, the output values become very large positive numbers. Equivalently, we could describe this behavior by saying that x approaches positive or negative infinity. The f of x values increase without bound, and in symbolic form we could write, as x approaches plus or minus infinity, f of x, remember f of x and y are the same, f of x approaches infinity. So, show the graphs of x cubed, x fifth, and x seventh, which all are power functions. Figure 3 shows, so right here, they're all power functions with odd whole number powers. Notice these graphs look similar to the cubic function in the toolkit. That's not it. Sorry. Let's come back here. This is it. This one right here. These graphs look similar to the cubic function in the toolkit. Again, as the power increases, the graph flatten near the origin and become steeper away from the origin. Oh, and there it is. I should have made a note that it had it on the next page. These examples illustrate the functions in the form f of x equals x to the n, reveal symmetry of one kind or another. We see that even functions are in the form f of x equals x to the n, where n is even, are symmetric about the y-axis, and in this in figure 3 we see that they're symmetric about the origin. For these odd power functions, as x approaches negative infinity, x decreases without bound. As x approaches positive infinity, x increases without bound. So as x approaches the negative infinity, so negative infinity is this way. As x approaches negative infinity, then these numbers get more negative. So as x approaches negative infinity, the y values approach negative infinity. This is positive infinity. As x approaches positive infinity, as it goes this way, f of x or y increases without bound. And so that is as x approaches infinity, then f of x approaches infinity as well. The behavior of the graph of a function as input values get very small, x equal to negative infinity, and get very large, x approaches infinity, is referred to as the end behavior of the function. We can use these words or symbols to describe the end power. Figure 4 shows the end behavior of the power functions in the form x equals k to the nth power. N is a non-negative integer depending on the power and the constant. So if you have an even power, as x approaches negative infinity, f of x approaches infinity, and as x approaches infinity, f of x approaches infinity. Alright, so if you have an odd power, this is the way it goes. If you have a negative constant, this is how it goes. And if you have a negative constant on an odd power, that's how it goes. So if you have a power function where n is a positive integer, identify the end behavior. You're going to determine where if it's even or odd, determine where the constant is a positive or negative, and then use this figure 4 to identify the end behavior. So this says, describe the end behavior of the graph of x to the 8th. Well, I know that it's going to be an even power, and there's no negative, so I know it's going to come up. So as x goes to negative infinity, y, or f of x, goes to infinity, and as x approaches, that's negative infinity, so x approaches infinity. Doesn't matter if it's going left or right, their numbers are going to get big and go to infinity. And that's the graph of x to the 8th right there. So describe the end behavior of this graph. And it's f of x equals negative 9. So the constant equals negative 1. So we know that it's going to be reflected across the x-axis from the regular cubic function. And so we would go back to this here, and it would follow these rules right here. So we would say, as x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches infinity. You can't equal infinity. Okay, so how do we identify a polynomial function? I know you were up all night wondering that. That probably kept you from sleeping. I know none of you were up worrying about that, but that's okay. I'm just trying to be funny. So this is a generic way to write a polynomial function. So you notice that, like, this is a sub 2 x squared, so these always match. Anytime you have something up here as an exponent, it's anything down here is a subscript, and it's a form of naming, and we talked about that a little bit when we were talking about slope. So this is a sub n times x to the n. Anytime you have a dot dot dot, that means there's stuff missing in between. Okay, and each a is a coefficient, and it can be any real number, but it can equal 0. Okay, so we're going to talk about which one of these are polynomials. And so let's see, so this one is, because this would be 6x to the 4th plus 4, and this would be and this, I can multiply this in to be negative x cubed plus 4x, so that can be written like that. This one right here cannot be written like that, so it's not a polynomial function. We often rearrange polynomials so the powers are descending. That's really, really important, okay? And sometimes if they're missing one of them, we even put a placeholder in. I'll show you. When we get to that, I'll show you how to do that. So given a polynomial, let's talk about its degree and leading coefficient. The degree is the highest power, and the leading coefficient is the number that sits in front of the variable with the highest power. So what we're going to do here, this is out of order, so I'm going to rewrite it as negative 4/3 plus 2x squared plus 3. And so now they're in order. I can say that the degree is 3, and the leading term is this whole thing, and then the leading coefficient is this number, negative 4. For g of t, that's 5, 3, t. So it's in order. So it's a degree 5. The leading term is this entire thing, and then the leading coefficient is equal to 5. See, this one is out of order, so h of p is negative, let's put a little bit more room there, negative p cubed plus 6p minus 2. So its degree 3, its leading term is minus p3, and its leading coefficient is a negative, so it's negative 1. So I keep referring to the end behavior of polynomials. Knowing your degree is helpful in helping us predict its end behavior. To determine its end behavior, we're going to look at the leading term of the polynomial function. Because the power of the leading term is the highest, that term will grow significantly faster than the other terms as x gets very large or very small, so its behavior will dominate the graph. For any polynomial, the end behavior of the polynomial will match the end behavior of the power function consisting of the leading term. So here's one, and it kind of looks like to the fourth, but it's because of these things subtracted from it, that's why it does wonky stuff right here. And this, well, it's negative, so it flips down, and it's kind of like, it has the same end behavior as a upside down parabola, but because of this right here, that's why it does. This right here is because what's added and subtracted here in the middle. So here's another one. It looks like a cubic, kind of, but then there's weird stuff in the middle, but it has the same end behavior. Same with this guy. So describe the end behavior and determine a possible degree for the polynomial function in figure 7. Here's figure 7. Here, as the inputs values get very large, the outputs increase without bound, and as it gets very small, they decrease without bound. So as x approaches infinity, the function values approach infinity, and as x values approach negative infinity, the function values approach negative infinity. This also has the shape of an odd degree power function that has not been reflected, so the degree of the polynomial creating this graph must be odd, and the leading coefficient must be positive. Whew, that was a mouthful. Okay. So, given this general form of f of x, express the function as a polynomial in general form and determine the leading term, degree, and end behavior of the function. So, well, the first thing I'm going to do is I have to multiply it. So I'm going to multiply these two together. I get f of x is equal to minus 3x squared, and when I FOIL that, I get x squared plus 3x minus 4. And then I take this into all three, and I get 3x to the 4th plus 9x cubed plus 12x squared. And so this is my leading coefficient. My degree is 4. So it's even. I didn't write my negative down, shame on me, as when I copied it down. My leading, so this is my leading term. And my leading coefficient is negative 3, so we know that it's going to be pointing down. Okay, it's going to look something like this. So as x approaches infinity, f of x will approach negative infinity, and as x approaches negative infinity, f of x will also go to negative infinity. Alright, so now we have things called, we're going to look at that local behavior and turning points. So this graph is bebopping along, coming up, and we have hit an intercept. We go straight through, and then we get here, and it turns and starts going back down. So this is a turning point. Comes down and hits a vertex, goes down, then oops, hits a turning point because it starts going up again, and then immediately hits a y-intercept, and it goes back up to an x-intercept. So a turning point of a graph is a point which the graph changes direction from increasing to decreasing or decreasing to increasing. The y-intercept is a point at which the function has the input value of 0, and the x-intercepts are the points on which the output value is 0, and that's why we call them zeros as well. So given a polynomial function, determine its intercepts. So we've been doing this for a while now. Determine the y-intercept by setting x equal to 0, and determine the x-intercepts by solving the input values that yield the output value of 0. So I have this function, x minus 2 times x plus 1 times x minus 4, written in factored form for your convenience. That made me laugh the first time I read that. Determine the x and y intercepts, and it is more convenient because otherwise you would have to factor it, and it would take you twice as long. So for the x-intercepts, you're going to let y equal to 0. So I get 0 equals x minus 2, x plus 1, x minus 4. So we know that x minus 2 equals 0, or x plus 1 equals 0, or x minus 4 equal to 0. So x equals 2, x equals negative 1, or x equals 4. So that's the point 2, 0, negative 1, 0, and 4, 0. And then we have for the y-intercept, we're going to let x equal to 0. So I get y is equal to 0 minus 2 times 0 plus 1, 0 minus 4. So it's minus 2 times 1 minus 4, and that gives me 8. So I have 0, 8 for my y-intercept. And there is the graph of what we just did. Okay, and you could have also put that equation exactly how it was presented to you in Desmos and clicked on the intercepts, and they would have given you the same information. Alright. So determine the intercepts of this function with factoring. So I'm going to, and determine the x and y intercepts that, I don't think that line's supposed to be there. So I'll make sure it's not on your notes. Alright, so this is x squared, I have a 5 and a 9, and I need the bigger number to be negative, equal to 0, x squared plus 5 equals 0, or x squared minus 9 equals 0. This is the difference of squares. I like these. And this is x squared equals negative 5. And so, square root of both square root of both sides, plus or minus I square roots of 5. And x minus 3 equals 0, x plus 3 equals 0, x equals 3, x equals negative 3. These are only ones that are going to show up on the graph because imaginary zeros don't show up on the graph. And then we're going to do the y-intercept. We're going to let x equal to 0. And so y equals 0 to the 4th minus 4 times 0 squared minus 45. So that's the point 0 minus 45. And here is a graph of that. It's kind of, well, the scale of x and y are not the same, so don't love it, but that was in your book. So now we talk about intercepts and turning points. A polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So if I have, well, let's think about it. If I have x squared, looks like this, right? Well, some form of x squared. And it's, then n is 2, right? And there are at most 2 intercepts and 1 turning point. So without graphing this function, determine the local behavior of the function by finding the maximum number of x-intercepts and turning points for f of x. Okay, so I know that my degree is 10. So I have at most, I can have less than that, 10 x-intercepts. My handwriting is atrocious, I apologize. 10 x-intercepts and 10 minus 1, which is 9 turning points. And why we say at most, because some of those intercepts can be imaginary and they won't show up on the graph. So what can we determine about this polynomial in front of us? Well, this one has, he has 2 intercepts, right? And there's 1, 2, 3 turning points. So this would suggest 2, so as it says here, the graph has 2 x-intercepts suggesting a degree of 2 or greater, and 3 turning points. So you probably would say, because remember n minus 1 turning points, so if n minus 1 equals 3, n should equal 4. Okay? Alright, so given this function, determine its local behavior. So we're going to have x-intercepts at minus 4x equals 0, x plus 3 equal to 0, and x minus 4 equal to 0. So x equals 0, that would be 0.00, x equal to minus 3, and x equal to 4. Y-intercept, let x equal to 0, so that would be negative 4 times 0, 0 plus 3, 0 minus 4, so it all equals 0, so this will be your x and your y-intercept. So, and it's 1, 2, so degree 3. So at most 2 turning points. Alright, here's some more videos if you need them. Contact me if you need me. On to the next one.